Good afternoon everyone, it's Joe at JAS LR here and we have got a problem. Yes we do, we have a problem, and that problem is the car is running perfectly. The problem with it running perfectly is it was meant to be a non-runner and we were meant to diagnose it this afternoon. Go and do a little diagnostic journey, do some fault code, do some tests. But it's running. This does not help us. So what have we done? What can we do? I can turn it off because it's noisy. We have read fault codes. A note on checking fault codes. So our diagnostic socket is down here underneath the dash. This lead goes to that box. That box is a CAN breakout box. It's quite expensive. It's got a diagnostic plug on one end, the box at the other end, and then it's got a diagnostic socket on it as well for me to plug Autologic into. That really expensive box, I'm using it as an extension lead. Yeah, not tire roll. So we checked fault codes with Autologic in the boot because that's where I wanted to start playing around and looking at this car. The only fault codes that we had were some lean running fault codes. It may not help us, it may help us. This car's got LPG, it may just log lean running fault codes for the fun of it because of the LPG. We're going to ignore it for now. We're going to focus more on what the customer complained of, how they described the fault, which was they were driving along and it cut out. It cut out, but they said when they tried to restart it, it did run, but very badly, with not exactly a misfire, but stumbling a lot, almost like it was running out of fuel. So we're going to focus on the only thing that we know about this car is that it stopped running and it sounded like it was running out of fuel. The dashboard says it's got fuel in, like the gauge on the dashboard says it's got fuel in. I believe it's got fuel in. We don't believe in this case we've got a faulty fuel gauge, for example. We believe we have got something else wrong. With that in mind, the first thing I've done it already now, is a fuel pressure test. Tell you what, I'm just going to get a torch so we can actually see what's going on here. Oh yeah. Right. Beautiful. Precautions. Right, petrol engine. It's fuel injected engine. Ignore this for now and these pipes. That's all part of the LPG installation. We're going to concentrate on this metal pipe. That's our petrol fuel rail. We get fuel fed from the in-tank fuel pump up to the fuel rail where it's supplied to the injectors. Here's one injector in the centre of the screen there, clipped onto the fuel rail. So it's 8-cylinder, 8 fuel injectors, 1 fuel rail. Fuel is supplied to this. It should be supplied to a 3.5 bar. That's about, I think it's about 50 psi, but bar is what it specs, so we're saying 3.5 bar. We've got a nice test port here. There you just unscrew the cap, plug in our fuel pressure gauge. We will turn on the ignition and we'll see what pressure we get. Ignition's on. Three bar. Not 3.5, but not nothing. Let's just try that engine running, see what happens. That's engine running. Still 3 bar. So we have some fuel pressure, not no fuel pressure, but some fuel pressure. I'm going to leave the test gauge on for now, while we look at something else. So I thought perhaps we were going to be looking at a fuel problem, and pretty much everything fuel related, most of it at least, is here in the back. At least everything we want to look at for now. Other things you'll have to take my word on. Just give me a second, I'm going to move the camera around. Right, so we've got Autologic in the back, we've got multimeter ready just in case we want it. Some other of our favourite tools spread around. We've also got Pico ready just in case we want that. For now, first thing we're going to do, Autologic, ignition's back on. We're in component activation, just going to go general. Down here we've got a fuel pump relay, just third up from the bottom. I can command it to turn on. And when I do that, I can hear the click. I'm just going to move you over here while I do the same thing again. See if you can hear it. On again, off again. Now, I don't know whether you can hear that, but I can hear that. I can hear the relay clicking, and I can actually hear the fuel pump running. I'm going to see if we can go and listen to the fuel pump, because it doesn't actually sound all that good. So, on. I don't know how well that shows up on the video, but you can hear it squeaking a little. You can hear it almost like thudding, kind of cutting in and out. So it's not looking good for a fuel pump at this stage. We haven't got the right amount of fuel pressure that we should have, even though it does run, and it doesn't sound too good either. But we can't. I wouldn't want to condemn it just on that. And well, it's Sunday afternoon. I want to do a little video. How else can we test this fuel pump? So what's down here in this corner is we've got our rear fuse box, which also contains some relays, a main power feed from the battery, and some fuses along the bottom. We've also got, I'm going to try and put a copy of this on the screen because it might be easier for you guys to see it. Here is our favourite, again, wiring diagrams. So if we start at the top, we have a, I don't know whether you can see this with reflections. Is that any better? Maybe, we'll go with that. So battery feeds our passenger compartment fuse box, which feeds our rear fuse box, which is this fuse box. That's our big red wire. That's this red wire. So I'm going to turn that back on. And this is the fuel pump wiring diagram only. So this is missing a lot of stuff. If you ever see on Land Rover wiring diagrams, at least, rear fuse box here with a dotted line around it, that means that there's something else to this fuse box that isn't shown, but it's only showing you the relevant stuff. The dotted line means it's only showing you relevant stuff. Same here. Dotted line around there, dotted line around engine control module, dotted line around the fuel tank. But this is our rear fuse box. For now, we've got, now I don't know if you can see this stuff, so as I say, I'm going to try and put this on the screen, but here we have fuse 15, 25 amp fuse, and we have fuel pump relay. That relay takes power, or would take power from that 25 amp fuse through the relay down this wire. So we've got two wires here, but we're ignoring this one. This is diesel only, whereas this one is relevant to diesel and petrol. Feeds our in-tank fuel pump, which then earths through its own dedicated earth. That relay is switched by this other circuit, which is fed power from a fuse 51 10 amp fuse in the passenger compartment fuse box, and it is ground controlled by the engine control module. There's no point checking that fuse, passenger compartment fuse box. Why is that? Because we know it must work if we can command the pump on and off. And there's obviously no problems with the ground control side of the circuit, no problems with the engine computer, because again you turn it on and off and it turns on and off. We also hear the fuel pump running when we're running the engine, so again the engine control module is capable of controlling the circuit, and the switching side of the circuit is being provided by power by the fuse, otherwise it wouldn't switch, so that's fine as well. Remember our fuel pump runs, so we know we've got some power running through this fuse. The other week I think we used the amazing test light, or circuit load tester. We're not going to use it this time, we're going to do this a different way. It could be, we could have a problem where we're supplying the correct voltage to the fuel pump, but it's not able to draw the required amount of current through the rest of the circuit. It's not that, I don't think, but again we're going to prove that in a different way this time. We could also have an earth fault, again if we're not able to spin the pump fast enough, for example. That could be any problem with the power supply side to the fuel pump, rather than the switching circuit, the power supply side, including the contacts in the relay, to be fair. But we're going to rule that out a different way. Again, control side is absolutely fine. We can turn it on and off as we like. We can hear the relay clicking, we can hear the pump start and stop. There's no point checking that fuse. There is no point checking that fuse. I'm sticking my neck out, we're saying that. So what are we going to do? Well, we're going to use Pico, because we're going to pull that that relay out. We're going to put this kind of fake fuse in, if you like. It's got the correct pins on the back, which might look weird to you, and you're right, and I'll tell you why in a second. We've got an on-off switch on the top and a loop, which we are able to carry out tests on. Yeah, that looks like a normal, I say normal, it looks like a regular 4-pin, actually 5-pin relay, but ignore the 5th pin, ignore the middle pin. It looks like a normal relay. However, despite saying Range Rover on the back, this is a BMW. And to remind you about that, the relay even says BMW on it. So, why is that relevant? It's relevant because a regular 4-pin relay would have the power to the relay and the power to the circuit, as in you've got your switching side, which we don't have on here because we've got a switch on top. We've got a switching circuit on a normal fuse would be this pin and this pin, and our power supply would be top or bottom, and the power to the fuel pump would be the opposite, would be top or bottom or top, whichever. However, BMW are idiots, and they organised their relay pins, or at least they did at this time, in a different way. So instead of having, right, I need these two, I also want to use the back of my bit of paper here. So, can't do it. This is that drawn big so that we can all see it. We have power from the battery. Oh, that's our red lead. This one, 25 amp fuse. The switch inside the relay, as in the contact inside the relay, and then our wire going to the fuel pump. Here we have our control side, 12 volts in, ground controlled by the engine control module, and I've drawn our numbers on there. Those are the standard numbers that you would see on a relay, 85 and 86. Control side 30, power supply 87, supplying the load or the fuel pump in this situation. And normally as I say. 30 and 87 would be those two, top and bottom. However, BMW 30 and 87 are these two, and control side are these two. When we realise that, we also know we have to use the dedicated BMW, one of these, which we're now going to do. In fact, no, we're not. We're going to use this again and just prove that we have the correct powers and everything at our connectors in here. So, time for multimeter. I'm going to turn it on. I'm going to leave it on that screen because it's quite easy to see. I'm going to turn that off. So, power supply to the relay. We've got the battery charger on this, so 13.8 volts, that's good. That's our pin 30. We also want 85. .8 as well. We've got our ignition on, so we're going to see something at this pin. And that is our ground controlled circuit going back to the engine control module. 3.6 volts. But we don't really want to know voltage, we want to know resistance to ground. So resistance to ground here in open air, massive resistance to ground, out of range. If we go in there again, massive, we still have huge resistance to ground. There is no ground path at that pin. Now will that stay in there? Yeah. Watch what changes when we turn the fuel pump on. Perfect ground path, 2 ohms, 2.5, and then it turns off. So that all works okay. We just want to check one more, which is the top one, which is the feed to the fuel pump. Should be nothing, and it is nothing. So that's all fine. And what we're going to do? Oh, that's right. We're going to plug, not that one. That will fuck us up. So that's in there. Now we can control it with this switch. Fuel pump on, fuel pump off, fuel pump on, fuel pump off. And Pico. We've got on screen here, this is an example waveform of what we see of what we want to see for a fuel pump. Nice regular. This is current, by the way. We've got current up the side, time along the bottom. This is not very fast, it's quite fast. Each one of these is 2 milliseconds, so across the screen there is 20 milliseconds. That's what we would want to see. It's a generic fuel pump, so our current draw between 4 and 6 amps. Regular repeating waveform. We're measuring current. So this is as the motor does some work, gets harder to turn, and then less hard to turn, then harder to turn, less hard to turn. Remember, this isn't a lot of amps. This is between 4 and 6, or not even that, between 4.5 and 5.5, and it's only an example. So ours may not look anything like that, but what we're looking for is a regular repeating waveform. I'll explain what that means later on. So, low current amp clamp, I'm going to turn it on 20 amps, we're going to zero it. So what we're going to do first is we'll just start Pico recording. In fact, I've done that wrong, so let's just stop a second. This might take a few seconds. Just going to load that up again while I show you current clamp again. So current clamp, turned it on, 20 amps. We're going to hook it and we're going to leave it down there. That's what we're going to do. We're not going to get ahead of ourselves. So, back to Pico. It comes with this already zoomed in. So we're only getting 10 amps up the side. I don't want that. I want only one. No zoom. I'm going to see the whole 0 to 20 amps, which we can. And I'm just going to reference waveform. That's this menu, reference waveforms, channel A, and that will keep it on the screen. So we're now recording, but we've kept our reference on the screen, which is going to help us. We are going to zero the amp clamp and connect it up to our circuit. No amps, we're looking at this blue line. This is our original line, our original example waveform. Along the bottom there, nothing, which is good. And we're going to turn on the fuel pump. You can hear it making noise. And what on earth is that? That looks a lot like a faulty fuel pump. It doesn't look like a good fuel pump, put it that way. Even though this fuel pump, have a listen, can you hear it? I don't know if you can hear it, I hope you can, because it sounds horrible. Even though it is now it's capable, nearly 3 amps anyway, nearly 3 bar, sorry. Let's have another listen. As I say, I don't know if you can hear it, so I won't keep you there too long, but that's not regular, it's not repeating, it's not very pretty. We're just going to stop it and turn that off. So what can we really learn from this? We can learn there's something wrong with our fuel pump, but there's more we can learn from this too. If I drag this down here, this cursor, to that highest peak, remember this is only 20 milliseconds, the last 20 milliseconds before I press stop. But at that last peak, we were able to draw 13 amps. So the fuel pump is capable of drawing at least 13 amps from this electrical circuit. That says to me that our circuit, all of it, is fine. We've got good power, we've got good voltage, we know that, sorry, to our fuse. We've got good voltage to our fuel pump relay, and the rest of the circuit, all of the circuit, from the battery to the passenger compartment fuse box to the rear fuse box, to fuse the relay, everything, the earth, everything, the whole circuit is capable of supplying 13 amps. Just going back through the buffer, a little bit more there. $14 amps. If we had a circuit problem, we wouldn't be able to draw that amount of current from the whole circuit. We can prove it a bit better if you like with this, but genuinely there is no need. Remember that draws about 4.5 amps, I think we said the other week. And this is showing we're capable of drawing 14 amps. But we want to see this, and we're seeing that. There's something wrong with our motor. Now, we don't have a new fuel pump here, so hopefully during the week when I get one in, get it fitted, I'll just rerun this test with our amp clamp, with Pico, and maybe with the fuel pressure gauge as well, just to prove that the whole circuit works fine. Which doesn't really explain why this car came in not running and running badly and running like it was about to run out of fuel. All we can really think, all I can guess, all I can surmise is that the fuel pump is faulty. We know that for sure. With waveforms like that, you don't run an engine properly. I'm going to guess that the fuel pump itself got stuck, got jammed, just got electrically stuck, if you like, on a bad commutator segment, or just physically stuck. and that is why it stopped. That's why it wasn't if you got stuck, it wasn't able to supply the correct fuel pressure. Without the correct fuel pressure, engine stops. It's that simple. I'm gonna do a little test actually, just a live test for you. I'm gonna turn the fuel pump back on. .8 bar. What we're going to do now is start the engine. And that is not the whole test, don't worry. Still got 2.8 bar. Now I don't know how quickly this next bit will go. So I'm going to be a bit quick. I'm going to grab a torch and I'm going to turn the fuel pump off. And it stopped already. It still says 2.8 bar, but the engine stopped. Let's see if it will start back up and see what it sounds like if it does. So this is fuel pump off. Will the engine start? Kinda, but not. The answer is, it stops really fast and then it won't restart, almost like it ran out of fuel. Almost like the fuel pump was dead. We've turned the fuel pump back on again. And it starts back up. I'll tell you what we are going to do. Right, that's a more accurate representation of fuel pressure. Just let it bleed up a little bit. I'll try and be a bit quicker this time. Ready? Off. Engine stops. Well, that's an obvious thing really, I guess. You turn the fuel pump off, the engine stops. But it kind of proves our theory that a dicky fuel pump that got stuck or stopped and started rather than just running would be enough to cut the engine off. It would then be able to, with that fuel pump off, remember, is it off? I forget. Yeah, still off. Starts up, cuts out, starts up, keeps cranking like it ran out of fuel. Yeah, 2 bar. What we're saying then is, I need to get a fuel pump. Might be quite obvious, but I need to get a fuel pump. I need to fit that fuel pump, and then as I say, we'll try and carry out this test again and finish this one off. For now, that will do. 6 o'clock, Sunday evening. That's right, Sunday. Just doing a little bit of recording for you guys. This week could be quite busy. I don't know when I will be able to fit this fuel pump. Hopefully soon. And then carry out a bit of a test again. Edit, upload to YouTube. And we'll see you guys later. Don't forget, I'm going to say this, I never say this. Like and subscribe. See you guys later. Thanks. Bye. Alright, it's Monday afternoon. We've fitted a new fuel pump now. Car runs perfectly. I knew it was running before, but obviously when it first came in it wasn't running. We've got Pico hooked up again. I'm just going to show you what a good waveform looks like on the brand new fuel pump. So just a note on setup again. We've got low amps current clamp on a little breakout relay which is switched off. Pico's showing us, this is our reference waveform, the one we had before, a known good example that Pico give us. In a minute we're measuring nothing, 0 because obviously fuel pump's turned off, Amps up the side, 0 to 20. We're on a 2 millisecond per division time base, so 2 milliseconds, 4 milliseconds, total of 20 milliseconds across the screen. I will change that later on to show you one other thing we can do, but for now let's just Pico's capturing. I'm just going to turn on the relay, and there you go. And this is our reference waveform, and this is current. Sorry, the current waveform, the waveform I'm measuring right now. As you can see, that's very different with this brand new fuel pump to the waveform that we got yesterday with the faulty one. I'm now just going to pause Pico, turn the relay off, and we'll just do a few quick measurements. So we're drawing a maximum of 13.5 amps, a minimum of 11.93 in a delta, that is the difference between the two, of 1.1. We can look at a couple of other things to do with the shape of the waveform, and to do that I'm going to do what I said I would do a second ago, which is just get rid of all of our markers, and I'm going to change our time base now to 5 milliseconds. And press capture again. I'm actually going to get rid of, no I'm not, we'll leave the reference waveform on there for now. We're on 20 milliamp, yeah, 5 millisecond time base again. So we're going to turn relay back on, and you get exactly the same as before, except slightly closer together, obviously because we're looking at a longer period of time, for a reason I might add. Pause it again. Turn the relay off. Right, the reason why we're doing this is this is current flow through each commutator segment of the electric motor part of the pump. It is regular, and it is repeating, and it is uniform, which is three things that we look at to give us an indication that this is a good waveform. We're just going to look at a couple of things we can do. So each one of those pulses, so 1 pulse, 2, 3, 4, 5, 6 and so on, as I say, each pulse, each current draw, so from there, the bottom of that trough to the top of the peak, if you like, is the current increasing as the motor draws current through one commutator segment. As it drops off the back, that's as that commutator segment rotates past the brushes and current falls. The next one is when the next commutator segment lines up with the brushes, it starts to draw current again, and similarly on and on and on. Now our motor, if we remember, rotates, and it rotates constantly, which is I'll tell you what, we'll go on to that in a minute. Excuse me. We'll just go on to this first of all. So as I say, it's regular and repeating, and if we go through it, let's just make a note of, this is tricky. Right, let's look at this one here, which is, it's slightly lower than the previous one, and it's slightly lower than the one that comes after it, but the one that comes after it is lower again than the one that comes after that. So 1, 2, 3, 4, 5, 6, 7, 8, and then we start repeating again, slightly lower, slightly higher, but slightly lower than this one. 1, 2, 3, 4, 5, 6, 7, 8, and again these two are lower. So what we're saying there is, and I'll just drag some cursors across the screen here, from there to there, to this point, this slightly smaller one, just before it, to just before the same one a bit further on, that from there to there is one rotation of the motor, one complete 360 degree rotation. if you could pick that up from any point you wanted. I mean, that was just quite an obvious one. Those two that are slightly lower, and we pick the first one. The two that are slightly lower, pick the first one. Two that are slightly lower, pick the first one, and so on. Excuse me while I just change the music a second. Let's see what we got. Bit of Sabaton, why not? So that's one rotation, that would be another, that would be another. We can count our commutator segments, we can count how many segments there are. 1, 2, 3, 4, 5, 6, 7, 8. We can do that. That's quite simple. But what else can we note? So we're measuring time across the bottom. The time from one cursor to the other is 13.33 milliseconds. We could do some maths and we could work out how many times this motor is rotating per minute. If it takes 13.33 milliseconds to do one rotation, or we could just let Pico do it for us. 4,500 RPM. It's quite simple like that. Now that's with the fuel pump submerged in fuel, supplying fuel under pressure to the fuel rail. In free air, if you like, that would spin much faster, but 4,500 RPM for this motor with the engine off is pretty good RPM. It's kind of, that's almost like the motor stalling. It's not stalling, but it's that's a static load, if you like. That no fuel is being returned, it's just creating pressure, nothing else. We like Pico for things like that, it tells us useful things. We do have a little written down database of good fuel pump current draws and RPM, for example. Now if the current draw was high and the motor speed was low, that could indicate to us a blockage in the fuel system downstream of the fuel pump. So that's current high and RPM low, sorry. That would be a restriction downstream of the pump. If you imagine low current draw and high RPM, you could potentially have a restriction before the pump, so a blocked gauze in the tank, for example. And remember, you can check that with absolutely no disassembly. Okay, in this case we took a relay out. We removed one relay and we could have found reason to suspect a blockage in the fuel pump, a blockage in the fuel pipe or similar. That's what we like about things like this. We can get an idea of the condition of various components without actually doing any disassembly whatsoever. I think that was nearly all I was going to go on to say. I'm just going to show you, I've got some pictures somewhere of commutator segments. I may have stuck them in the video already. If not, I'll stick them in now and just do some little annotations and maybe a separate narration. But we don't like narration, narration's bad, even that's what I do all the time. Yeah, so there we go. Couldn't get away with all of them. Here is a picture of a motor. It's a pretty generic motor. For all intents and purposes, all we're really going to talk about is the A and the B on this picture. So A is the commutator. Each kind of segment of that is each commutator segment. That is mounted centrally in the motor. It spins along with that kind of central C part, if you like, the armature. That is the motor. That's what the pump would be attached to. That whole central section is what spins. B then is the brushes, or one of the brushes. The other one is there at the left hand side. If you imagine B then, the brushes, that's where our power is supplied to the motor. As the brush touches against a commutator segment, the power can pass into that commutator segment and round the windings in the armature in C. It can then pass out of the windings at the opposite commutator segment and out of the motor via the brush, the opposite brush. That completes a circuit. As the current is flowing into that part, through those windings, it generates a magnetic field, and that magnetic field is what spins the motor. Specifically, it spins it in a direction, or in one direction, and as it spins, the commutator segments that were lined up with the brushes move out of contact with the brushes, which then allow the next commutator segments, the next pair of commutator segments, to line up. The magnetic field is generated again, and it spins a bit more, lines up with the next commutator segment, spins a bit more, and as each commutator segment lines up and draws current, that's where we see our upslopes on our picograph on the waveform, and as it drops off the segment, that's when we get our current decreasing on pico, and then as the next pair of commutator segments line up and the circuit is made again, that's our current increasing. That's electric motor theory, the very, very basics of it for a DC motor. I think now back to the workshop. This Range Rover is fixed, new fuel pump. You can see the waveform is what we were saying earlier, it's uniform, repeating, and whatever else I said. That's another one fixed. So it's time to say it one more time, because I never say this, so you're getting it twice in one video. Like and subscribe, tell your friends. See you, bye.